All right, so we just did normal line. For the most part, pretty straightforward. Find your derivative, plug it in there. What we're gonna do now is our more 5.4 bit, and this is where it is gonna be a bit new. Now, part of it is gonna stay kind of the same, but this is gonna be, let's go white, please. This is gonna be local applications of derivatives. You kind of want to think like, basically, what does a derivative mean? And importantly, a derivative is most of the time talking about a precise position, a precise point, right? It's your instantaneous rate of change. That's why we're using local. We're not really thinking big picture on derivatives. We're thinking about small picture for this. So here's what we're going to do. Let's start with a function y equals, let's make up some function here, 3x squared plus 8x minus 5. Let's take two derivatives of this. So let's go for y prime, 6x plus 8, and let's go for y double prime, 6. Again, nice Monday morning derivatives. We definitely don't mind that. Now, in calculus, you need to be well-versed. You need to understand what is the original and what is it good for? What is the derivative and what is it good for? What is the second derivative and what is it good for? And the third derivative, we don't really care. It's kind of like, I almost like to think about this like it's like your 3 dimensions, you know? And then the 4th dimension, like, exists, but like, it's kind of confusing to think about. It makes things way harder. But 3 dimensions isn't that bad. So you have to know what these 3 do. Now, your original here, this is your f of x. This helps you find the position of the function, which again is no surprise. We've been using the original function since Algebra 1. We just did this for our tangent line. We just found the position of that point. You take the x, you plug it in, it gives you the y, it gives you the output, it gives you the range. Cool. For this next one, now, y prime tells us our gradient. It's our instantaneous rate of change guy or girl. Of course, your gradient is your slope, it's your rise over run, it is increasing or decreasing. So maybe I'll do something like this. Not all that important, but it's nice because when we talk about the second derivative, we don't, at this point, I don't think you guys have any idea what this is good for. Does anybody know what the second derivative is about? Cool. The second derivative is about concavity. And after we write that, you probably still don't really know what it's good at because it's a word that's really never come up before in math. However, concavity does sound like a word you'd learn in science class when it comes to lenses, concave versus convex, and concave is the one that's like a cave, right? And so your concavity has to do with a curved shape, and really using your hands, I'm telling you, is super successful. Your concavity of a graph is whether it's curved up like this or whether it's curved down like this. So at any instant, your graph might be curved up, or it might be curved down, or of course, it might be right in the middle of those two. So when it comes to concavity, a positive graph will look like that, and a negative graph will look like that. And so considering our function that we just randomly made up and we randomly did the derivative for, if you consider the concavity, right now, is the concavity positive or negative? Positive. And actually I say right now because there's no more x values. So this concavity cannot change. It will be 6 forever, which means it will be positive forever. And if you think about our original, which is a parabola with a positive a value, it looks like this forever, and it will never switch to concave down. Just like our second derivative is positive, it will never switch to negative. So concavity normally is something that sounds crazy, but we can pull it into our knowledge like pretty quickly. Let's look at a little chart we're gonna make, and then we're gonna do a question similar to how we did it before. So let's draw a line that goes across. This doesn't have to be huge, but I'm gonna kind of cut it in half, and then in half and in half, so that I get kind of 4 columns here. I'm just gonna kind of leave this one blank. I'm gonna go with f of x, f prime of x, and f double prime of x. And then over here, let's talk about when is this greater than 0, less than 0, and equal to 0. So when we do this, and we're talking f of x, it's almost like so simple that it can be weird to write down, but when is f of x greater than 0? How does that look on your graph? Above what? The origin. Yeah, the origin is a point, so they're not all above the origin. So I'm gonna say above the x-axis, which is what you mean, but I'm just being picky math teacher guy. Yeah, so this is y above the x-axis. And of course, same thing for the less than, except for it says the y is below the x-axis. And then equal to 0. What happens when it's equal to 0? It's on the x-axis. And what's a better way to say when something's on the x-axis for a function? Yes, it's an x-intercept. Now, typically, is it that useful? Where is a function greater than 0? Not really. Is it that useful? Where is it below? Not really. Is it that useful to find x-intercepts? Typically, yes. This is a pretty nice thing here to find when the original is equal to 0. So cool. That one's pretty useful. The other two exist, but they're not super useful. So what about f prime? What is going on when f prime is greater than 0? We kind of already said this before. It's increasing.
Good morning, Mr. Joseph.
Good morning.
I'd like to talk to the students one more time about the AI program that we use here, actually Chesapeake, for all schools to monitor what's written or typed on Chromebooks. Students, just be aware, this is not just at school, this is also at home and on the weekends. If you type something that's inappropriate.
What have you guys been Googling on the Chromebooks? Come on.
If we find that something is inappropriate, you could face possible disciplinary outcomes. We don't want this, which will give you a good heads up that the things that are written on Chromebooks are monitored, not just here at school, but also at home and on the weekend. So please be mindful of that. Take care of what you write. Thank you. Bye.
Appreciate you, Mr. Joseph. Always a great reminder. Don't be a weirdo on the Chromebook. All right. What happens when f prime is equal to 0? Right, so your f prime is your gradient, and this is a positive gradient, and this is a negative gradient. And when your positive gradient is getting closer to 0, it looks like that, which is flat across. So another way to say this would be that your slope is 0. Now, if we think about our graph, what is happening at our graph when the slope is 0? Okay, so where do we have a slope of 0? Is it 0 right here? What about right here? What about right here? Yes. So when our tangent line is 0, what happened on our white graph? It was a minimum. Is our tangent line 0? Well, I kind of missed, but there you go. Is our tangent line 0 there? No. What about there? No. What about there? No. But what about there? Yes. And what is that? So when our first, when our first derivative is equal to 0, how does that show up on our graph? As a maximum, as a minimum. And there are some other words I want to make sure that we catch here. So I'm going to write in this box, eventually, here we go, maximum or minimum. We can also call this extrema, which is a little bit of like an algebra word more than a calculus word, but extrema is one word that means both maximums and minimums. And same thing with this word, stationary point. Stationary point just means maximums and minimums. Now, why do we need that? Why can't we just say maximums and minimums? Well, actually, the graph that I've drawn for you is nice. It's not too bad, but it's repetitive. What if I draw you a graph that looks like this, but then looks like that, right? That's something that could happen for sure. And when we consider our tangent lines, negative, negative, 0 at a minimum, nice, positive, 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 0. Would you consider that a maximum or a minimum? Not really, right? A maximum is when it goes from increasing to decreasing. That's what makes a maximum. Here, it's gone from increasing to increasing. And so this can't be considered a maximum or a minimum. But at this point, is it going up? Not exactly, right? It's got a tangent line of 0. And so that's why stationary point makes a little bit more sense, because it's stationary for just a second and then it goes back to increasing. So that's why a lot of times, honestly, it's like just some teachers like to say stationary points. Some assignments like to say stationary points. It just means find it where it's equal to 0. So all of those things, kind of be ready for those. And lastly, what we've just learned today, our second derivative. So if it's greater than 0, it is called concave up, because it's concave up, because it's a bowl that's up. And then of course, no surprise, when it's less than 0, it's concave down. And when is it equal to 0? Well, when we have concave up and we also have a concave down, you have to kind of transition from one to the other at some point. And so right here, where my fingers touch, this is called the point of inflection. Now, the point of inflection is one of these things that is actually less easy to see or less easy to find than some of these other things. So if I draw you a picture and I say, okay, here's our graph. Do we have concave up portions? Do we have concave up down portions? So surely in between there, we've switched over. However, identifying the exact location of when they change is something where, if I said put one little dot here and I shut the door, you guys would come up with maybe 3 different spots for each of the 3 different of you. However, maximums is easy, right? Maximums, boom, we got it. Minimums, boom, we got it. So point of inflection can be a little bit harder to just kind of spot really quick. The way that they'll kind of fix that for you is they'll just say something like A, B, C. Which one of these letters is the point of inflection? That way it's like, oh, okay. It's definitely not A, it's definitely not C. It's somewhere in the middle, B works. So just look out for that kind of stuff. It is theoretically easy to look for, to consider. You just think, oh, well, this one's concave down, and this one's concave up, maybe right there. But again, we can't be extra. It's really tough to be super confident about exactly where that point of inflection is when you're just looking at the graph. But when you take the second derivative and set it equal to 0, it can be very easy to find. Now, let's finish. This will be the last thing we'll do here. Let's finish by considering our original thing that we found, okay? And let's find when is f of x equal to 0, when is f prime of x equal to 0, and when is f double prime equal to 0. All of these things are pretty useful. F of x equals 0, that's your x-intercepts. F prime of x equals 0, that's your stationary points, your maximums, your minimums. And then f double prime, that would be your points of inflection. Now, for the original one, when we find where is our x-intercepts, bad news, we just randomly made this up. And so, pretty good chance this is not going to work super nicely. Can we factor this -15 to, no, we cannot. And that means we'd have to use quadratic formula, which really isn't all that bad. Let's do it because we're IB kids. Negative b plus or minus square root b squared minus 4ac, 64 minus 4ac. Well, c is negative, so let's make it a plus because we have 2 negatives. 4 times a, which is 3, which is 12, times 5, which is 60, all over 2a, which is going to be 6. 64 plus 60 is going to be 124, which certainly can be simplified a little bit. 124, which is 2 times 62, which is 2 times, yeah, you can just toss that down, 31. Cool. So I think I'll give you those papers in just a second. I think the best way that we could, oh God, come on. Let's say that we have 31 with a 2 out front because we had those 2 2's, which is square root of 4, which is 2. And maybe even better, we could simplify the 8 and the 2 and the 6. Best answer negative 4 plus or minus square root 31 over 3. Those are our two zeros. A little annoying, but we can find them. And you will maybe have to use a quadratic formula when we do a question. F prime equal to 0. Typically it's easier because our equation has degraded down a little bit. So we've degraded down and it's only 6x plus 8. Set that equal to 0. Subtract the 8. Divide by 6. I'm getting negative 8 over 6 or negative 4 over 3. Now that is a stationary point. Now, immediately after finding that stationary point, we can't determine if that's a max or a min just by getting this number. Now, if we consider other things, if we consider that we know it's a quadratic with a greater than 1, so it's a u facing up. So yeah, this is going to be a minimum. The second derivative would be our stationary, or our point of inflection. If we set our second derivative equal to 0, does 6 equal 0? No. Does it ever equal 0? No. Do we have a point of inflection? No. And again, that makes sense because we're just a U-shaped graph. There's no inflection points there to find. Okay, I think it's good enough. Just considering all three of those different things, let's look at, here we go, here you go, Colin, you might be a little burnt out. We're gonna do one of these questions, and then the rest of it, you'll have to finish everything I've given you for homework. SL2, we got it now, test. We want to do 5.4. We got it. Okay. Find any stationary points and determine their nature. Determining their nature meaning, is this a maximum? Is this a minimum? Let's figure that out. So for A, go back to black. Step 1 for finding stationary points is, what are we doing? Basically identify how many derivatives you need to take to get there. Stationary points is that the original, the first derivative, or the second derivative? First. So we need the first derivative. F prime of x is equal to 3x squared plus 6x plus 3. Cool. Step 2. Do we need this to be greater than 0, less than 0, or equal to 0? We pretty much, all the math we ever want to do is setting things equal to 0. So awesome, let's set this equal to 0. And now that we're equal to 0, we're going to be allowed to...
That one's different from one.
Is that a different one?
Yeah, ours is the same for parts x cubed plus 3x squared, but ours is minus 9x.
Is this one in your packet? Well, maybe the notes just got deleted. And so I think when I did the HL kids, I gave them different questions for notes so that they would have more homework. So maybe that's why easier for us. I hate that it only shows me like the first 2 letters of the name. All right, we want the day 12 homework 13.5.4. This one, x cubed plus 3x squared minus 9x. All right. Well, sweet. Well, now we'll have to go twice as fast to catch up to where we were. Whoa. All right, same start. A, stationary points, f prime of x is equal to 3x squared plus 6x minus 9. Set it equal to 0. Because we're equal to 0, we are allowed to say, you know what, 3, 6, 9, those all divide by 3. So let's just divide everything by 3. X squared plus 2x minus 3 equals 0. Can this factor, or do we have to use the quadratic formula? Anybody got it? Okay, it factors. What does it factor to? Minus 1 plus 3. Our two stationary points are going to be at x equals 1 and x equals negative 3. Now it says find any stationary points and determine their nature. This is a 6 marker. We definitely have not done 6 marks worth of work so far. We did a derivative, that was the easiest thing ever, and we did algebra 2 or algebra 1 even, factoring. So where are the rest of those marks coming from? We need the stationary point, and right now we have the stationary x value. Right now we know there's a graph that has a stationary point here somewhere, but we don't know it's right there. So for this, we want to take the 1, plug it back in, and get our kind of place. Now, where are we going to take that 1 and plug it into? The original, so that we can find the position. So we're going to find f of 1, which is going to be 1 cubed plus 3 times 1 squared minus 9 times 1. That's pretty easy. It's all 1s. 1 plus 3 minus 9. It's going to be 4 minus 9, negative 5. That's my y value. I also need to find f of negative 3. This is going to be a little bit uglier. Negative 3 cubed, negative 27. Negative 3 squared is positive 9 times 3 is positive 27. And then another positive 27. 27 minus 27. So this was going to be just 27. That's my other y value. Okay, so now I have my points here. I have x value 1, y value negative 5. And I have x value negative 3, y value 27. Okay. I still haven't quite earned all those points because find any stationary points and determine their nature. I've got those points. I don't know maximums or minimums. Now, I could, if we think about this graph, we've got an important stationary point at 1, negative 5, 1, negative 5. And we also have an important point at negative 327, negative 327. But we have that same issue of, I know that this one looks like a maximum, but maybe it's got one of these things going on. So we can't guarantee that it is a maximum. I know that this one looks like a minimum, but we can't kind of guarantee. So when it says justify your point, doing okay? Yeah, cool. When it says justify your point, you have to somehow prove that this is a maximum or a minimum. So 2 things that we can use to prove. For a maximum, I thought I just changed that. Okay. For your maximum, a maximum is either where you go from increasing to decreasing, if you can prove to me that before that you were increasing and after that you were decreasing, well, that means you're a maximum. The other way you can prove that you're a maximum is if you are concave down. If you can show me that you're concave down, that's also going to be a maximum. Now, which one of these do you think is easier to do? Just off your gut feeling, which one do you like better? I like concave down. The reason I like concave down, one, when you're working with the second derivative, it's normally easier than working with the first derivative because every time you take a derivative, things are getting smaller and kind of worn down. Two, for increasing, decreasing, you have to prove before and after those two different places. However, for a concave down, you have to prove right at that value. So you just pick the value you're choosing, plug it into the second derivative, and go from there. So when it comes to verifying maximums and minimums, I like concave down. I'm going for concave down. Or it could be up. That would be a minimum. Again, if you feel like you need to write on the paper the minimum things, it's the opposites. You guys got it. So let's take these. Let's consider the second derivative. F double prime of x, which would be the first derivative, obviously again, which would be 6x plus 6. So again, like Bryce was saying, like I was saying, second derivative is nice because that is just worn down even more. Then we're going to take these stationary points and use their x values to check them at the second derivative. So f double prime of 1, 6 times 1 is 6, plus 6 is 12. And this 12, being a positive number, tells me concave up, which tells me that we have a minimum. So this point here is a minimum. We do the same thing. F double prime of -3 is equal to 6 times -3 plus 6. That's -18 plus 6. That's -12. That negative number means concave down. That tells me max. So this point right here is a max. Okay. Before we do those other two, which I'm going to do much, much faster than we did these two, this one. This is basically what we're trying to learn today. It is that there are those three different levels, the original, the first derivative, and the second derivative. And a lot of time when you do these questions, you have to kind of jump around, right? For just point A, we started with the original, we took the derivative equal to 0, we found those 2 points, then we went to the original function to find the y values, then we went to the second derivative to use the concavity. So we're using all three different things for their three different values. So that's what we're up to. And if you get that, then there's not, that's where all the difficulty is. B, find any points of inflection. Cool. Well, points of inflection would be where the second derivative is equal to 0. So let's write B here. F double prime of x equals 0, which is 6x plus 6 equals 0. Where would that be? Algebra 1. Anybody got it? What'd you say? Yes, -1, right? Cool. Now, that is not the point of inflection. That is the x value where it exists. So let's go back to the original and plug that in. That would be f of -1 is equal to -1 cubed plus 3 times -1 squared minus 9 times -1, which is -1 plus 3 plus 9, which is 12 minus 1, which is 11, -1 comma 11. Now, when it comes to points of inflection, there is no increasing, decreasing. There's no maximum, minimum. There's no concave up, concave down. You're either a point of inflection or you're not. So when we find the point of inflection, we don't have to decide, is this a max or a min? Is this up or down? That's it. That's the point of inflection. We got it. It says justify your answer. That's where the second derivative is equal to 0. Right? That's how we found it. I don't think there's any more that we need to do to justify that we're good on that. That is just the point of inflection. And the last thing says sketch the graph. I already, did that wrong, sorry. We already kind of did this, but let's just get it up here really quick. It was 1, -5. It was what was the other? Maximum -327. So way up here. It was -111, which is right here. This is a max. This is a min. This is a point of inflection. It says on C, sketch the graph. Okay, it doesn't say include the maximums, include the minimums, include the point of inflection, include the x-intercepts. If that question says include the x-intercepts, we haven't found those yet. We'd have to solve for those using the original function. But this one, it just says sketch. So you know what? One last mistake. Here we go. Maximum looks like that. Minimum looks like that. Point of inflection is where these two bowls should meet. Maximum meets the minimum. There we go. Good enough sketch, labeled good enough. Whatever. All right, I think I've talked plenty enough about this using the 3 different pieces. This is equal to 0, that's equal to 0. You guys got it.